Hello everyone and welcome to Pure Chapter 11.8b of Edexcel's second year course in A-level mathematics. So why have I called it 11.8b? Well, subchapter 11.8 deals with finding areas underneath and in between curves. 11.8 focuses mainly with finding areas where curves are given in standard form, whereas actually the chapter also mentions about finding areas underneath curves and in between curves which are given parametrically. And this is going to be the focus of this video here. So 11.8a was non-parametric. This one here focuses on finding areas where curves are given parametrically. So this is why I've denoted this as 11.8b. So now that's made clear, let's get warmed up with a couple of examples. So question 1 is a U-sub, question 2 is a parametric integration question from chapter 8 to get in the mood for having to integrate using parametric equations. So pause the video now and try these on your own, and then press play when you're ready to see what the solutions are. So, assuming you've had a go, let's have a look together at the solution to warm up question 1. So question 1, it says to use substitution u equals 1 plus root x to show that this integral here can be transformed into an integral to do in terms of u. So it says here to work out p and q essentially. Well, it doesn't. It says where p and q are constants to be found, but the implication is to find q and p. So let's just go from basics. So we're told that u equals 1 plus root x. The first thing we need to do is to find du by dx. So if we differentiate u with respect to x, 1 disappears. That's x to the power of a half. So the half comes to the front, the power of x goes down by 1, so we get half x to the minus half. Therefore, rearranging to get dx in terms of du, essentially, if we were to, we can think of it as cross-multiplying essentially, but just by doing a rearrangement. Times both sides by dx, then multiply both sides by 2. So we're going to get 2 du equals dx x to the minus half. But if I divide by x to the minus a half, what I'm going to get on the other side is x to the positive a half. So that's going to transform to 2x to the 1 half du. So that's what dx is. So I can get ready to replace dx in terms of what it is in terms of du. Next up as well, what we need to consider is also the fact that x isn't given in terms of u. So from this bit here, once I know that u is 1 plus root x, if I were to square this, I can see that u squared, whoops, actually no, I won't do that. If I subtract 1 from both sides rather, I see that u minus 1 equals root x, just by subtracting 1 from both sides. That's a better move, actually. And then if I round square, so then x is going to be u minus 1 squared. So again, I can now also replace x with what x is in terms of u, which is u minus 1 squared. And of course, we're going to say that u itself is 1 plus x, sorry, 1 plus root x, so we transform that to this. So putting all those pieces together, we can switch an awful lot now. So essentially we can tackle it. So that was from x being 16, and this is from x being down to 0. So I had x all over 1 plus root x. With respect to x, we can now input these changes. So that's the same. Well, x we can change now with u minus 1 all squared. So let's just make that the change already. So we've got u minus 1 all squared on the top. The bottom, 1 plus root x, well, that's what we term to be our u. And then dx, we said, is the same as 2x to the half du. Now, you might be thinking now, well, I've got an x to the half to contend with here. But actually, that's not going to be the end of the world. We can deal with this okay, in fact. So what I'm going to do in a moment is just show you how we can deal with this x to the minus a half. So basically x to the minus a half is just the same as at the square root of x, and so actually we've got it already here, haven't we? I don't need to do any more work at all. So root x, which is x to the 1/2, is the same as u minus 1. Another thing we need to consider is the limits of u. So we've gone from x being 0 up to x being equal to 16. So the first thing we need to do is consider what u would be, what u corresponds to if x is these two limits. If I do a little table here for x and u. So when x is 0, so I'm doing that over there actually. So when x is 0 rather, u is 1 plus the square root of x. So when x is 0, u is 1 plus root 0, which is just 1. And when x is 16, u is going to be 1 plus the square root of 16, which means 1 plus 4, which is 5. So now we can change this to u limits of u being equal to 1 on the lower limit and u being equal to 5 on the upper. However, we can now also replace this x to the half, as I said. So we've got x, which is u minus 1 all squared. We've got 1 plus x, which is u here, and then we can change the x to the half with another u minus 1. So essentially we're going to have it in the next step. So finishing off, that's going to give us from 5 up to 1. Now I'm going to have two lots because of this constant 2 here. U minus 1 squared times another x to the half, which is another u minus 1. That's going to give u minus 1 cubed. All divided by u with respect to du. So that's the integral which I wanted to show was the case. So now for part B, what we can now do is actually integrate this. So that's part A. Part B is to actually integrate it. And so the next step is to say from 5 to 1 of the wrong colour of this integral. We can actually do this by taking that 2 to the outside. Now u minus 1 all cubed, we can actually expand this all out. Okay, so what I'm going to do here is do u cubed, which of course is u cubed. This is the binomial expansion essentially. You can do it longhand if you really want to, or you can just use a pattern of the binomial expansion. For the next one, we're going to have then 3 choose 1, which is just 3 lots of u squared multiplied by 1 lot of minus 1. So that's going to give us minus 3 u squared. The u terms, we're going to have 3 choose 2 u to the power of 1, and then minus 1 to the power 2. Minus 1 times minus 1, of course, gives positive 1. And so then we're going to have positive 3u. And the final term is going to be minus 1 cubed. Minus 1 times minus 1 is positive 1, but multiply again by minus 1 gives negative 1. All that's over u with respect to u. Now what we can do here is divide all of this denominator, sorry, all this numerator by the u on the underneath. So we've got from 5 to 1. Keep doing the wrong line. Rather silly. So u cubed divided by u becomes u squared. In fact, I don't know that line at all. So I've got u squared minus 3u plus just what a normal 3 is, then minus 1 over u, all with respect to du. So then I'm going to have two lots of quite an awkward thing in the middle. So if I input the, if I integrate u squared, I'm going to get a third u cubed. Integrate minus 3u, I get minus 3 over 2u squared. 3 goes to 3u. And integrating minus 1 over u, that's going to integrate to minus ln mod u. in between the limits of 5 and 1. So, we've input when x is going to be 5, 1/3 u cubed, that's going to be 125 over 3. U squared is 25, so minus 3 over 2 times 25, that's going to be minus 75 over 2. Plus 3u, that's going to be 3 times 5, which is 15. Minus ln 5. And that's the upper limit. But if I'm going to subtract away when x is 1, that's going to be 1/3. That becomes minus 3 over 2. Plus 3 times 1, which is 3. And then minus ln of 1, which is just 0, so I don't even need to include that. So, comparing what I need it to have in terms of a form, I need it to be minus b ln 5. So looking here, I can see it's going to be minus 2 times ln 5, so that's okay. If anything I need to do really is to take care of working out what the constant term is. So let's do this on the calculator very carefully. So, first of all, we're going to have 125 over 3 minus 75 over 2 and plus 15 equals this. I'm going to minus off in this bracket here for 1/3 minus 3 over 2 plus 3. And that gives 52 over 3. But of course, we've got 2 lots of that because of this term on the outside, and then multiply that by 2, so get 104 over 3. So we've got 104 over 3 minus 2 lots of ln 5. And that's my final answer for question 1, part A and part B. What about question 2? So I have a curve C1 with parametric equations, x being 22 cosine t and y being 2√5 sine t, as shown here, this ellipse. And then this curve C1, the ellipse, meets circle C2 with equation x squared plus y squared, which is 130. So we're told that at 4 distinct points, as shown here, the curves intersect each other. One of the points S lies in the 4th quadrant, so S is here. And we need to find the Cartesian coordinates of S to 3 significant figures. So let's first of all spot that we've got this in parametric, x and y, and that what we can do is substitute these expressions in for x and y into this equation of the circle. If we do that, we can then solve for what t would have to be to satisfy both equations. So if we do that as our first step, so if I let x be 22 cosine t, which of course is what it is, so 22 cosine t all squared, plus y squared, where y is 2√5 sine t, all that squared, that must equal 130. So next we can expand these brackets. So 22 cosine t, 22 squared gives 484. So that's going to give 484 cos squared t. 2 squared is 4, √5 squared is 5, so I'm going to get 4 times 5, which is 20. Sine squared t equals 130. I could do this all in terms of sines or cosines, not as a mixture. So I'm going to choose to replace sine squared with 1 minus cosine squared to get it all in terms of cosines. So if I leave 484 cosine squared t as it is, but then the sine squared, using cos squared plus sine squared is 1, I'm going to replace that with 1 minus cosine squared t, which will be 130, of course. So then if I expand this out, I get 484 cos squared t plus 20 minus 20 cosine squared t equals 130. Simplify, so 484 cosine squared minus 20 cosine squared, 464 cosine squared t, then take 20 from both sides, that equals 110. Divide both sides by 464. So cosine squared t equals 110 over 464. Then to work out what cosine is on its own, square root both sides. So cos t, I'll talk about plus or minus roots in a second. Before I do that though, let's just think about this quadrant here and what I want x and y to be. So in this quadrant, where I've got point S, that's where x is positive. This is where y is negative. And so if x is positive, cos t must be positive, and if y is negative, then I want sine to be minus. So we can use a class diagram is what I'm going to get at in a moment. But first of all, let's do cosine t, which is a square root of 110 over 464. We can get one value from it here. So square root 110 over 464. That gives 0.486, and so on, and so on. So that's going to be the first value, which you can write down here. So cos t, we've got, is 0.48689, and so on. So that's what we have so far. At this point as well, in case I wasn't clear earlier, it's worth just mentioning that I don't need to consider plus and minus for cosine t here when I square root, based on this fact that in this fourth quadrant, cosine t needs to be positive, because x is positive in this quadrant. So cosine, because it needs to be a positive value, to make x a positive value, I don't need to consider the negative square root. So I can be comfortable with the knowledge, I can just consider simply cosine t as being this 0.48689 figure. So to work out what t is, I can now do arc cos. So therefore t, essentially it's cos minus 1 or arc cos, whichever you want to think of it as. So cos minus 1 of 0.48689, etc., etc. So if we try this on our calculator, so we've got this answer there for cos, so cos minus 1 of that. Make sure you're in radians, which of course we are. 1.06226, and so on. So that's what t is. However, I want sine t to be a negative. So at this point, what it might be worth doing is just reminding ourselves of the good old class diagram. So here's one I made earlier. So if t were 1.06226, this would make sine to be a positive value. Whereas actually I don't want sine to be positive, I want sine to be negative, but cosine to be positive. So the actual quadrant I'm wanting is this one here. And so the angle for t, what I'm wanting for t, is actually this blue one here, which will be 2 pi minus the 1.06226, and so on and so on. So t equals that, which we're going to end up rejecting, because this will give an answer where sine is positive, which we don't require. We require this one. So, or t, this one down here, which is 2 pi minus the answer we've just obtained. So 2 shift pi minus that answer, 5.2209. Give a few more figures for accuracy, in fact. 22986. So we're going to reject the first one, because this is where sine would be a positive value, which we don't want. So that's what we've got for t. So now we have that for t, we can now go forward and finish off. So what I want here is the coordinates of S. And so x is going to be 22 cosine of t. So it's going to be 22 cosine of 5.2209 and so on. So if I do this for x, so 22 cosine of that answer, and remember I want this to 3 different figures, so that's going to be 10.7, and y, if x is 22 cos t, y, remember, is 2 root 5 sine of t, which will be 2 root 5 sine of 5.2209, and so on and so on. So let's just get that figure back, what we had, which was this one for t. So if I just type in now 2 root 5 sine of 5.2209 22986, and we get minus 3.91. Piecing these together, I've now got what the coordinates of s is. So s must be when x is 10.7 and y is minus 3.91. So now done the warm-up questions, let's have a look at the main topic of today's lesson, which is using integration, so using parametric equations to integrate integrals. So how to do this, how to use parametric integration to find areas under curves. So we can also find the area underneath a curve or between curves if both curves are given in parametric form. It's usually easier to integrate with respect to the parameter. Typically it's t, sometimes it might be theta, for example, but normally it's t. And we can do this by taking the following steps. So first of all, differentiate x with respect to the parameter, usually t. So it's find dx by dt or dx by d theta, whatever. Next, we need to change the limits of integration so that they're now in terms of a new variable t, not in terms of the original variable x. And then we need to use the fact that integrating y with respect to x is the same as integrating y with respect to dx over dt. With respect to dt, essentially these dt's on the bottom and top cancel, just leave with y dx if you like. So we can transform y dx into this form to then integrate the original integral in terms of t. So let's apply it now with a couple of worked examples. So worked example 1, I have a diagram showing a curve C, which is given in parametric form by the two equations x is natural log of t and y is t plus root t, where t is defined between 1 and 10. The finite region R is bounded by curve C for straight lines with equations x equals 1 and x equals 2 and the x-axis itself. So first of all, for part A, we're asked to show that the area of R is given by this integral here. So let's set to it. So for A, we're told that x is the natural log of t. Therefore, let's take dx by dt, which of course just be 1 over t. Therefore, by rearranging to get dx in terms of dt, we can hopefully see here that dx is simply going to be, if I then multiply both sides by dt, basically dx is going to be 1 over t times dt. So I can switch out what dx is. Next as well, we can now pretty much just go forward and integrate. So, or set up integration at least. So the area of R is going to be the integral from when x is 1 from x is 2 of y dx. Now of course y is t plus root t, and dx I've worked out in terms of dt, so we can fill this in as well. So we've got t plus root t times by 1 over t dt. And now we can also consider the limits of integration, changing from being in terms of x to being in terms of t. And dx, of course, is this thing here. So what are the limits going to be in terms of t? So let's just think about this in terms of what x is. So x goes from the limit of being 1 up to 2. So when x is 1, x must be the natural log of t. And so basically t here must be e, because the natural log of e is 1. And when x is 2, 2 would be ln of e squared. So t must be e squared when x is 2. So the lower limit, 1, corresponds to t being e. The upper limit of 2 for x corresponds to t being e squared. So now I can simplify this as our final step for part A. So it's going to be the integral. So t2 essentially is e squared. t1 at the bottom is e. So then essentially I'm expanding these brackets. So t multiplied by 1 over t just gives 1. This is the same as t to the half. T to the half divided by t will give t to the negative 1/2. So I end up with exactly what I wanted to prove as required. This is what I wanted to show, and I've shown it to be that case. And I've worked out T1 and T2. I've stated these. In fact, I can't let's just say again, T1 equals E, and T2 equals E squared. Part B is now to actually take this integral. So, if I integrate this with respect to t, 1 integrates to positive t. T to the negative half, well, the negative half, add 1 to the power goes to positive half, and then divide by that new power. Dividing by a half is the same as multiplying by 2. So this becomes 2t to the positive 1/2. I'm integrating between the limits of e squared and e. And so when we do that, I'm going to get, first of all, e squared plus 2e, because the square root of e squared is just going to be e itself. So I get e squared plus 2e first, then minus off when t is e, that just becomes e plus 2 e to the 1/2, but I might just call it square root of e for now, because I'm about to give it in the final answer form. So that simplifies to e squared. In fact, I'll start underlining now, because it's going to be my final answer. 2e minus 1e, that's just going to leave with just, essentially just 1e. So we get 2e minus 1e, which is just e, and then minus 2 lots of root e. Finally, worked example 2. This time I've got a diagram showing a curve with parametric equations, x being theta minus 4 sine theta, and y being 1 minus 2 cosine theta, where theta is defined in between 0 and 2 pi inclusive. The curve crosses the x-axis at points P and Q. First of all, we need to find the value of theta at points P and Q. So for part A, at P and Q, that's when we're crossing the x-axis. And so we set y equal to 0 at those points. So we set y equal to 0 at P and Q. So if y is equal to 0, then we say that 1 minus 2 cosine theta equals 0, because that obviously is what y is. And so if that's the case, it must be that cosine theta must be equal to 1/2. So therefore, thinking about the exact trig values, cosine of what angle is going to give us 1/2? That's 60 degrees in old money. So in terms of, use your calculator if you want to, of course. In radians, that would be where theta is pi over 3, because pi over 3 is 60 degrees in terms of radians. Or it might be 5 pi over 3, which is 300 degrees Again, you could do a cast diagram if you really wanted to. But with two values where cos theta is equal to a half, between 0 and 2 pi, is pi over 3 and 5 pi over 3. And so which one of these thetas relates to P and Q? This is what we need to check now, each one. So when theta is pi over 3, that gives us that x is pi over 3 minus 4 sine pi over 3. If in doubt, just use a calculator for this if you really want to. Could do far worse. So, pi over 3 minus 4 sine pi over 3. So, whether it's coming out positive or negative, that'll tell us which one of P or Q this relates to. Well, that comes out to be minus 2.416 and so on. So that's looking like it's going to relate to P. And then the other one, and theta is going to be 5 pi over 3. That gives x as being 5 pi over 3 minus 4 lots of sine 5 pi over 3, which again we can work out in a similar way as before. This time let's go for 5 pi over 3 minus 4 sine 5 pi over 3. We get 8.7000. So quite clearly, that one's going to relate to Q, because that's where it gives x to be a positive value. So essentially we've got our answers of part A. So therefore, values of theta at P and Q. So at P, theta has a value of pi over 3. I'll underline this now because it's going to be our answer. And at Q, theta is going to be 5 pi over 3. So now part B, we can think about actually finding this area and working it out as a integral. So let's think about this next. So we need to prove that the area given is given by this integral here. So for part B, the area, of course, is going to be y dx. What we need to do first of all is to find dx by d theta. So I can say this is the same as y dx by d theta times d theta. So from this, we can piece together what this is going to be. And so dx by d theta, well, x is theta minus 4 sine theta. So differentiate that with respect to theta. Theta differentiates just to 1. 4 sine theta will differentiate to 4 cosine theta. So we get minus 4 cos theta. So therefore, dx is going to be 1 minus 4 cosine theta integrated with respect to theta. We're now at a stage where we can piece this together. So the area, so it's going to be the integral of y with respect to x. And so y is this thing here, and we've got dx now. We've shown that dx is the same as 1 minus 4 cosine theta d theta. So filling these parts in, and again the limits, we can do the limits too now, because we've shown from part A that when x is at P, that corresponds to theta being pi over 3, so the lower limit's pi over 3, and similarly the upper limit was 5 pi over 3. So y is 1 minus 2 cosine theta, and dx is 1 minus 4 cos theta d theta. So all we're doing there is just substituting in what y is in terms of the parameter and dx in terms of parameter theta. And so we're pretty much home and dry really now. The only thing is to expand this and simplify. We've stated theta 1 and theta 2, so that's absolutely no problem. So the next thing is just to simplify down to show it ends up being this. And all it is essentially is just expanding the brackets out. So 1 times 1 gives obviously 1. How many cosine thetas? Well, 1 times minus 4 cos theta, that's minus 4 cos theta. Minus 2 cos theta times 1, that's where we get the minus 6 cosine theta. And then 2 cosine theta, so minus 2 cosine theta times minus 4 cosine theta, minus times a minus, that's going to give positive 8 cos squared theta, all with respect to d theta. And so that's part B done. Part C, we now need to find the exact area of the shaded region. So we're almost good to go now. The only thing is, we've got an 8 cos squared theta to contend with, which causes a slight bit of difficulty. What we need to do here for the 8 cos squared theta, we need to replace it using a double angle formulae. So I'm just going to put it over here in a little box so it's out of the way, not causing any grief. So if I just put this box here, so it's nice and out of the way, I'll colour code the box in a nice pink. And then I'm going to show how we can switch this cos squared theta to something a bit nicer. So I'm just going to make a note, this is for part C. And so this is for C. Remember that cos 2 theta, that's defined as cos squared theta minus sine squared theta. Now sine squared is 1 minus cos squared. So if we remember, this is the same as cos squared minus 1 minus cos squared. That's the same as 2 cos squared theta minus 1. So from this line, we need to see that cos squared theta is the same as 1 plus cos 2 theta all divided by 2. So it's the same as, whoops, not an equal sign there. So cos 2 theta is the same as a half plus, make this box slightly bigger, plus a half of, so cos squared theta, yes, is a half plus a half cos 2 theta, that's what I mean to say. So I'm going to use this here. So for C, again, using what we've had above, the area, this I can say is therefore the integral of 5 pi over 3 from pi over 3 of 1 minus 6 cosine theta, and then the 8 cos squared theta, using the idea that cos squared is the same as a half plus a half cos 2 theta. I can now replace this, in fact, if I make this blob slightly bigger, if I can, there we go. That whole thing can be replaced. If I multiply this by 8, half times 8 gives me 4, then plus 4 cos 2 theta. So now we can simplify and then essentially just integrate. So 1 plus 4 is going to give 5. And that will obviously integrate to 5 lots of theta. So I've got 5 theta. Minus 6 cos 2 theta will obviously stay as it is. That's got no more cosines or anything to add on. But cosine integrates to positive sine. So minus 6 cosine theta will stay as a negative, that just becomes minus 6 sine theta when I integrate. And then similarly, cosine again still integrates to positive sine. So here we're going to get sine 2 theta, but because it integrates and have a factor of 2, we're going to need to divide by that 2. So we do the 4 here, but divided by 2, in the next step we're going to have 2 lots of sine 2 theta. In between the limits, of course, 5 pi over 3, down to just pi over 3. So, finally, all it is now is just a case of filling in these limits carefully and evaluating, making sure we don't make any silly mistakes. So 5 pi over 3 times 5, that gives 25 pi over 3, minus 6 sine theta. So again, if in doubt, let's just work this one out. So on the calculator, if I were to do now minus 6 sine theta, where theta this time is 5 pi over 3, and plus 2 lots of sine 2 theta, so that's going to be 10 pi over 3. Shift pi, all divide by 3. That gives us 2 root 3 overall. So I get 25 pi over 3 plus 2 root 3. Then the lower limit, when we use pi over 3, so 5 times pi over 3 is just going to be 5 pi over 3. And then this thing here, I can just use a calculator and just edit. Instead of 5 pi's, just go and change it to 1 pi. So 2 theta becomes 2 pi over 3, so I can change this on the top to a 2. And 5 pi over 3 is just going to become simply just 1 pi over 3. And that gives minus 2 root 3. So now I'm able to simplify and obtain the final answer. So 25 pi over 3 minus 5 pi over 3, that's going to become 20 pi over 3. And then I've got 2 root 3 minus minus, so plus another 2 root 3, so that's going to give 4 lots of root 3. And there we go. So I hope you found that useful in terms of how to integrate when we've got parametric equations to deal with. So thanks for watching that. I hope it's clarified some of 11.8 for you, when it's parametric and when it isn't. So practice for questions in the exercise which relate to the parametrics. Keep going, and you know where I am if you ever need any help. So keep going, and thanks again for listening.